lecture of the course Mathematical Aspects of Biomedical Electronic System Design. In this lecture, we will begin a new module, Probability and Random Variables. In the first lecture of this module, we will learn about random experiments, probability, conditional probability, Bayes rule, independence of events, etc. So let us begin today's lecture. Let me start with introducing random experiments. Any experiment whose outcome is unpredictable is referred to as random experiment. Experiments whose outcomes are unpredictable. For instance, we can think of tossing a coin, in which case outcome could be either head or tail. Tossing a dice, the outcome could be any number from 1 to 6. Arrival of customers, say at the branch of a bank. So number of customers that arrive in a day is not predictable. Or say lifetime of an electric bulb, it's unpredictable. Electric bulb. We study this notion of probability in the context of random experiments. Before I introduce probability, I'll introduce some other nomenclature. For instance, let me tell what is meant by sample space. Sample space, usually denoted by the symbol omega, is set of all possible outcomes. For example, when in tossing a coin, sample space is this set containing head and tail. Tossing a coin thrice, same coin, if I toss thrice, now my sample space is set of tuples of the type HHH, HHT, dot dot dot, etc. TTT. So there will be 8 such combinations. Say throwing a die, now my sample space will be 1 to 6. This is the set of all possible outcomes. Next, consider that we have a rectangular floor. Let's say here is a floor and its coordinates are AC, BC, AD and BD. I throw a coin on this floor, the coin lands somewhere, and the point where the coin lands is the outcome of my experiment. In this zone, the experiment is throwing a coin on a rectangular floor. In this case, my sample space is collection of all points, the form xy, where x is varying between A and B and y is varying between C and D. Okay. The next notion is that of event space. often called sigma algebra. An event space or sigma algebra, usually denoted by the symbol script f, is a non-empty collection of subsets of omega collection of subsets of omega with the following properties. First property is, if A belongs to this set, then A complement, that is omega minus A, should also belong to F. This property is called closeness under complementation. Closed under complementation. Second property is, if A, B belong to F, then their union also belongs to F. This is called closeness under finite union. Closed under finite union. The third property is, if the collection of sets ai greater than or equal to 1 belong to F, then their union also is in F. This is called closeness under countable union. Okay. Let's see a few examples of event spaces. For any sample space omega, the collection of empty set and omega is an event space. It can be checked that this collection satisfies all these three constraints. If omega is 1, 2, then a collection of subsets 5, 1, 2, 1, 2, this is an event space. Notice that this collection is also what we call power set of omega. Similarly, if omega is a 1 to 6, the collection 1 to 3, 4, 5, 6, empty set, and capital omega, this is an event space. Again, it can be checked that this script f satisfies all the three properties mentioned above. At this point, let us recall De Morgan's laws, set theory. According to these laws, if A and B are two subsets of the sample space omega, then complement of union of A and B is A complement intersection B complement. Similarly, the complement of intersection of A and B is A complement union B complement. Before we move further, let us observe a few more properties of event spaces that follow from De Morgan's law. De Morgan's laws imply that F is closed under finite intersection that is, if A, B belong to F, then intersection of A, B will also belong to F. F is also closed under countable intersection. That is, if I greater than or equal to 1 belong to F, then their intersection will also belong to F. The next notion is that of events. Elements of event space are called events. Elements of F are called events. In probability theory, we are interested in chances of outcome belonging to an event. In fact, chance of outcome belonging to an event is called probability of that event. Okay. If you are interested in probability of an event A, then the outcomes belonging to A are referred to as favorable outcomes. Let us formalize this notion of probability. We do it via introducing the notion of probability measure, or often called probability law. It is denoted by a symbol P, which is nothing but a function. P is a function from F to R that satisfies the following properties. The first one is P of A is non-negative for all A in F. This property is called non-negativity. The second property says P of the whole sample space, P of omega is 1. This is normalization. And the third one is, if I greater than or equal to 1 belong to F and they are disjoint, that is AI intersection AJ is empty set, they are pairwise disjoint, then probability of union of these events is sum of their probabilities. This property is called countable additivity. The above three properties together are also referred to as axioms of probability. Having defined sample space, event space and probability law, we can now define so-called probability space. The tuple omega f p is called probability space. Before we see examples of probability laws or probability spaces, let me make a couple of statements about the scenarios where omega is discrete set, or in particular it's finite set. If omega is discrete, we often take the power set of omega to be the event space. So though it could be any collection of subsets of omega that satisfies the three properties mentioned above, we often take it to be the power set. Moreover, if omega 1, omega 2 dot 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 omega n are elements of omega, then the singleton sets omega 1, omega 2 dot 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 omega n, they all will be elements of F, and in this case the probability of the set omega 1, omega 2 dot 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 omega n is simply sum of the probabilities of these singletons. This equality is often referred to as discrete probability law. Okay. If the sample space is finite, say it has n total outcomes and all the outcomes are equally likely in the sense that all singleton events have same probability, then probability of any event A will be number of favorable outcomes, that is number of elements in A divided by n. Let's see a few examples now. First, consider the experiment where a die is tossed. In this case, sample space will be, as we have already seen, 1 to 6. Event space will be power set of omega, that is collection of all subsets of omega. Probability of the singleton sets P of omega will be 1 by 6 for all omega in omega, that is probability of outcome being 1, being 2, being 3, etc. All these probabilities will be 1 by 6. On the other hand, if you are interested in probability of say 2, 4, 6, then following discrete probability law, it will be 3 into 1 by 6, which is half. Let's see another example. Now consider the experiment where a coin is tossed twice. Now the sample space is HH, HT, TH and TT. As before, the event space will be power set of the sample space. Probability of a event which is a singleton set, say HH, will be 1 by 4. So will be probability of other singleton sets, say HT or TH or TT. Now we learn a few facts about probabilities or probability laws. These could be easily verified. The first one says that if A is an event, then probability of A complement is 1 minus probability of A. The second one is a special case of first. Suppose we take A to be the whole sample space, then A complement is empty set. So probability of empty set is 1 minus probability of whole space, and this we know is 1 by the axioms of probability. So probability of empty set is 0. The third property says that if A and B are events such that A is a subset of B, then probability of A is less than or equal to probability of B. Fourth property says that if A, B are events then probability of A intersection B is less than or equal to minimum of probability of A and probability of B. The next property says that as before, if A and B are events, then probability of A union B is probability of A plus probability of B minus probability of A intersection B. All these properties can be easily verified using set theory. In particular, the fourth property implies that probability of A union B is less than or equal to probability of A plus probability of B. The next property says if AI are events, I is greater than or equal to 1, then probability of union of these events is less than or equal to sum of the probabilities of individual events. This property is referred to as union bound. A quick point before we move ahead. If for an event A, probability of A is 1, we often say that A happens or A occurs almost surely. In short, it's written as this. Let's see an example. Consider the random experiment of tossing a coin twice. Recall that in this case the sample space was HH, HT, TH, TT. Define event E as the first outcome being ahead. First outcome is head. In other words, this is the event HH, HT. Similarly, let us define F to be the event that second outcome is head. That is F is TH, HH. In this case, probability of E is 2 by 4, that is half. So is probability of F. Then following the above properties, probability of E complement would be 1 minus half, that is half. Probability of E intersection F will be probability of HH. Notice that this is the event E intersection F. So probability of E intersection F will be 1 by 4, and so probability of E union F, again following one of the properties above, will be probability of E plus probability of F minus probability of E intersection F, which will be half plus half minus 1 by 4, which will be 3 by 4. The next notion that we will see is of conditional probability. Suppose we have a sample space omega. There are two events A and B. So A and B are in event space, and B is such that probability of B is greater than 0. Notice that this is the event A intersection B. In this case, we are interested in conditional probability of event A given event B. Conditional probability of event A given event B has occurred, it is denoted as PA given B, and it turns out to be equal to PA intersection B divided by PB. Here we see why we assume PB is greater than 0. It ensures that the division is well defined. Let's see an example. Suppose a die is tossed and it is told that the outcome is at least 3. It is told that the outcome is at least 3. What is the conditional probability that the outcome is 6? Probability that the outcome is 6. Here, if I define event A to be the event that outcome is 6 and B to be the event that outcome is at least 3, then probability of A given B will be probability of A intersection B divided by PB. A intersection B is same as A, so this becomes probability of A divided by probability of B. This becomes 1 by 6 divided by 4 by 6. This gives 1 by 4. The next rule that we will see is called chain rule. As before, let us assume that A, B are two events. Then we can rearrange the terms in the conditional probability formula to deduce that probability of A intersection B is probability of A given B times PB. In fact, it also turns out to be equal to probability of B given A times PA. This equality is called chain rule. Let's again see an example. Assume that an urn contains 7 black and 5 white balls. Suppose we draw two balls from the urn without replacement. What is the probability that both the balls are black? We are interested in probability that both the balls are black. Let us define events A and B as follows. A is the event that first ball is black, and B is the event that second ball is black. Then probability of A is, see, there are 7 black balls and 5 white balls, so there are total 12 balls. Probability that I'll draw a black ball is 7 by 12. Similarly, probability of B given A can be computed as follows. So given that the first ball was black ball, now there are only 6 black balls, so there are total 6 plus 5, 11 balls, out of which 6 are black. So given that the first ball was black, the probability that second one will also be black will be 6 by 11. Now I can use chain rule to compute probability of A intersection B, which will be simply product of PA and PB given A, and it turns out to be equal to 7 by 22. Next we will see a rule A very important one referred to as Bayes rule. As before, assume that A and B are two events such that probability of B is strictly positive, then probability of A given B is probability of A intersection B divided by probability of B, which can be written as probability of A intersection B union probability of A intersection B complement. This can further be rewritten as probability of B given A times probability of A divided by probability of B given A times probability of A plus probability of B given A complement times probability of A complement. This equality is referred to as Bayes rule. Let's see an example. Suppose there are two urns. First contains 2 white and 7 black balls, whereas the second one contains 5 white and 6 black balls. We also have a coin, so we flip a coin and draw a ball from the first urn. If the outcome of coin toss is head, and draw a ball from the second coin otherwise. Second urn otherwise. Okay. We are interested in the probability that outcome of the toss was head given that a white ball was fetched. What is the probability that the outcome of the coin toss was head given that a white ball was fetched? To answer this question, let us again define events W and H as follows. W is event that a white ball is fetched. And H is the event that outcome of the toss is head. Clearly, probability of H is half. So is probability of H complement or probability of tail. Probability of W given H, that is given that the outcome of coin toss was head, what is the probability that a white ball would be faced will be 2 by 9. Similarly, probability of W given H complement would be, there are 5 white balls and 6 black balls, so it would be 5 by 11. Now we have to compute probability that the outcome of coin toss was head given that a white ball was fetched. So probability of H given W, this will be probability of W times probability of This will be probability of H times probability of W given H divided by probability of H, probability of W given H, probability of H complement, probability of W given H complement. This will be 1 by 2 into 2 by 9 divided by 1 by 2, 2 by 9 plus 1 by 2 into 5 by 11, and on simplifying we get 22 by 67. Okay, so this is an illustration of Bayes rule. Let us now generalize Bayes rule to more than two events. Given an event A and events B1 to Bn, so I varying from 1 to n, such that the union of these events B1 to Bn is the whole sample space. Union of Bi, I equal to 1 to n is omega. Probability of A can be written as probability of A intersection Bi summed over I equal to 1 to n, which in turn can be written as I equal to 1 to n probability of Bi times probability of A given Bi. This equality is called law of total probability. Next, I can write probability of Bj given A to be probability of A intersection Bj divided by probability of A. This is using conditional probability. This in turn is equal to probability of A intersection Bj divided by summation I equal to 1 to n probability of A intersection Bi, which in turn can be written as probability of Bj given probability of A given Bj divided by summation over I to 1 to n probability of Bi, probability of A given Bi. This equality is generalization of Bayes rule to more than two events. Let us now move to the next notion, that is of independence. In the forthcoming lectures, we will study independence of random variables. So just to distinguish this notion, we explicitly say here independence of events. Let's define what we mean by independence of events. Say A and B are two events. These are called independent if probability of A intersection B is probability of A times probability of B. Notice that if probability of B is strictly positive, then A and B being independent implies that probability of A given B, which is probability of A intersection B divided by probability of B, turns out to be probability of A. Similarly, if probability of A is greater than 0, then A and B being independent implies that probability of B given A is probability of B. Let's see an example. Consider the random experiment of a die being rolled twice. Die is rolled twice. Let us define the following events. A is the event that first outcome is 4. B is the event that second outcome is 2. And C is the event that sum of the outcomes is 6. Then clearly probability of A is 1 by 6. Probability of B is also 1 by 6. C is the event 1 5 2 4 3 3 4 2 5 1. So probability of C is, the number of favorable outcomes is 5 and total number of outcomes in tossing a die twice is 36. So probability of C is 5 by 36. Let us ask the following questions. Are events A and B independent? To answer this question, let us observe A intersection B. A intersection B is the event in which the first outcome is 4 and the second one is 2. So this is A intersection B. Probability of A intersection B is 1 by 36. Only one of the 36 possible outcomes is favorable. On the other hand, probability of A times probability of B is 1 by 6 into 1 by 6, and again it's 1 by 36. So we see that probability of A intersection B is equal to probability of A times probability of B. So A and B are indeed independent. Now let's ask another question. Are events A and C independent? Okay. Again, if we see A intersection C, it turns out to be same singleton set 4 2. Probability of A intersection C is 1 by 36. However, now probability of A into probability of C, it becomes 1 by 6 into 5 by 36. This gives 5 by 216. Clearly, probability of A intersection C is not equal to probability of A times probability of C. So, A and C are not independent. Similar calculation reveals that B and C are also not independent. Let us now extend this notion of independence to more than two events. Given events AI, so I is ranging again from 1 to n, this events AI are called independent if probability of their intersection, that is I equal to 1 to n intersection AI, is product of their probabilities. There is another notion here, and that is of pairwise independence. So I ranging from 1 to n are called pairwise independent if probability of AI intersection AJ is probability of AI times probability of AJ for all pairs. This is for all I not equal to J. It can be seen that independence is a stronger notion than pairwise independence. What we mean that independence implies pairwise independence. On the other hand, if a collection of events is pairwise independent, that doesn't mean that those events will be independent as well. Pairwise independence does not imply independence. Let us see an example to illustrate this point. Suppose a ball is drawn from an urn containing 4 balls. And so those balls are numbered 1, 2, 3, 4. So 4 numbered balls. And define events A, B and C as follows. A is outcome is either 1 or 2. B is 1, 3 and C is 1, 4. In this case, probability of A equals to probability of B equals to probability of C is 2 by 4. Clearly in each case, out of 4 outcomes, there are 2 favorable outcomes. Next, probability of A intersection B, this is probability of 1, this is 1 by 4, and so are probability of A intersection C and B intersection C. Further, probability of A times probability of B is also half into half, that is 1 by 4. So we see that probability of A intersection B is probability of A times probability of B, and similarly probability of A intersection C is probability of A times probability of C. Probability of B intersection C is probability of B times probability of C. Finally, if we see probability of A intersection B intersection C, this set A intersection B intersection C is an empty set. So this becomes probability of empty set, which will be 0. And this is not equal to probability of A times probability of B times probability of C. Notice that this is 1 by 8. So clearly in this example, A, B, C are pairwise independent, but not independent. We observe the following important fact about independence of events. So fact, if A and B, events A and B are independent, then A complement B are independent, AB complement are independent, and so are A complement B complement are also independent. Let us now consider a few more examples. First example is, suppose a family has 2 children. Each may be a boy or a girl with equal probability. We are interested in the conditional probability that both are boys, given that at least one of them is a boy. What is the probability that both are boys given that at least one is a boy? We can again define events A and B as follows. A is the event that both are boys, and B is the event that at least one of them is boy. So it is BB, BG, or GB. Then we are interested in probability of A given B. We can use the conditional probability formula that says that probability of A given B is probability of A intersection B divided by probability of B. Probability of A intersection B is simply probability of A. Probability of A is 1 by 4. Since each one may be boy or a girl with equal probability that both are boys is half into half, that is 1 by 4. And probability of B is 1 by 4 plus 1 by 4 plus 1 by 4, that is 3 times 1 by 4. So the answer is 1 by 3. Let us see another example. Suppose a person alpha proposes a person's beta or gamma, each with equal probability, so each with probability half, to go for a movie. Person beta accepts a proposal with probability half, and gamma accepts a proposal with probability 1 by 3. We are interested in probability that alpha will watch the movie with gamma. What is the probability that alpha will watch the movie with gamma? Again, we can define two events. Event A is alpha watches the movie, and event B is alpha proposes gamma. Then probability of B is clearly half. Given that alpha proposes gamma, the conditional probability that A will watch movie with gamma is 1 by 3, because this is the probability with which gamma accepts the proposal. We are interested in probability of A intersection B, that is alpha proposes gamma and gamma accepts the proposal. So following chain rule, probability of A intersection B is probability of B times probability of A given B. So it is simply 1 by 2 into 1 by 3, which is 1 by 6. Let's see one more example. In answering a multiple choice question, a student either knows the answer or guesses it, or if he doesn't know, if he or she doesn't know, then he or she guesses it. Let P be the probability that the student knows the answer, that she knows the answer, and 1 by n be the probability that the answer is correct, she writes the correct answer despite not knowing it. Despite not knowing it, that is, she guesses correctly. We are interested in the probability that student knew the answer given that the answer is correct. What is the probability that she knew the answer given that she wrote correct answer? We can again define two events. K is the event that the student knows the answer, and C is the event that the answer is correct. We are interested in probability K given C. Towards this, notice that probability of K is P, probability of K complement is 1 minus P, probability of C given K, that is, the student answers correctly given that she knows the answer is 1, and probability of C given K complement is 1 by m. Now we can use Bayes rule to compute probability of K given C. It is probability of K times probability of C given K divided by probability of K, probability of C given K plus probability of K complement times probability of C given K complement. We know all these probabilities. Let us substitute these. So P times 1 divided by P times 1 plus 1 minus P times 1 by m. It turns out to be equal to MP divided by 1 plus m minus 1p. Before we end this lecture, let us see a few results on counting. These results will be quite useful in computing probabilities. The first one is on permutations. Permutations of n objects. Number of permutations of n object turns out to be factorial n, that is n minus 1 dot 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 up to 1. For instance, suppose we have 7 persons, A, B, C, D, E, F and G, and we want to arrange these people in a row. In how many ways we can arrange these people in a row? That is exactly the number of ways we can permute these letters A to G. Number of ways in which these persons can be arranged, and so this is factorial 7. The next result is on k permutations. K permutations of n objects. These are denoted by symbol NPK, and this equal factorial n divided by factorial n minus k. To see an example, Suppose the 7 persons in the above example have to join a queue. The queue has 3 positions. These 7 persons can come and join in any order. 3 out of 7 persons can join this queue. In any order. So this queue may look like A, B, C or B, A, C or D, E, F. Right? So each of this we call a queue configuration. So number of queue configurations will be equal to 7p3, which will be factorial 7 divided by factorial 4. Okay. Notice that here we are also concerned about the order in which these persons appear in the queue. So A, B, C is a different configuration than B, A, C. There are situations where we do not worry about the ordering. We only see the entities that are in the collection. This notion is captured by combinations. So we now look at combinations of K out of n objects. This is denoted by n choose K, or sometimes by simply nk, and this equals factorial n divided by factorial k times factorial n minus k. For instance, in the above example, if all 3 persons in the queue get the same gift hampers, all 3 persons in the queue get similar gift hampers. So either A, B, C may get gift hampers, or D, E, F, or A, E, F, right? So now we are interested in combinations of persons that get gift hampers. The ordering in the queue does not matter. So A, B, C and B, A, C will not be counted separately. So what is the number of combinations of persons in the queue? This will be 7 choose 3 equal to factorial 7 divided by factorial 3 times factorial 4. The above example can be seen as if we are dividing these 7 people into 2 groups, those that are in queue and those that are not in queue. Basically, we want to see in how many ways we can partition that 7 people in groups of 3 and 4 people. This idea could be generalized to more than 2 groups. So now we look at partitions to more than 2 groups, partitions of n objects into R groups, and say ith group can have ni objects, with the ith group having ni objects. The number of possible partitions is denoted by following symbol: n, n1, n2, nr in brackets, and it equals factorial n divided by factorial n1 times factorial n2 times factorial nr. For instance, in the above example, if we have to divide 7 persons in 3 groups, partition 7 persons in 3 groups with these groups having say 4, 2 and 1 members respectively. Then number of partitions equals factorial 7 divided by factorial 4 into factorial 2 into factorial 1. These were a few results about counting. This brings us to the end of this lecture. Thank you.